Okay, so in this video, we're going to learn about difference of squares. It's a different type of factoring pattern. So far we have learned GCF and grouping. Remember, GCF is greatest common factor, and grouping we use when we have four terms, which is just another application of GCF. Okay, so today is difference of squares, and we're going to learn difference of squares first, and then we're going to talk about how to kind of mix those with the others. So a few things. This name actually means something. So the first thing is we do this when problems have two terms. The next thing that you need to make a note of is that terms are separated by subtraction. So that is why we call it difference of squares, because difference means subtraction. So notice that this pattern is not going to work if the terms are separated with a plus sign, and I will kind of give you an example of that here in a minute. And then lastly, each term that we are given is a perfect square, which is why we also call it difference of squares. Now, what I want to do first is, before I show you how to factor some of these problems, I want to show you or give you some examples of perfect squares. So you know some of them, 1, 4, 9, 16. I think we've learned all the way up to 15. And we know these are perfect squares because 4 can be written as 2 times 2, right? 9 can be written as 3 times 3. 16 can be written as 4 times 4. Okay, I am going to pause the video and I'm going to complete this list all the way through 15. I would encourage you to do the same so that you have them written down. All right, so there's my list off to the side. I just thought it might be easier to stack it vertically. So let me give you some examples of other things that are perfect squares. X squared is a perfect square because it can be written as x times x. Let's see, 16y to the second is a perfect square because it can be written as 4y times 4y. Other things that are perfect squares, so they're not always, they can look different. Okay, so let me give you some examples of ones that look different. 9x to the 8th, all right? That can be written as 3x to the 4th times 3x to the 4th. We can also we can get more complicated by adding more variables. So 16x squared y to the 6th can be written as 4xy to the 3rd times 4xy to the 3rd. All right, so I would have these examples written down because you need to understand what perfect squares are so that we can then work with them. Okay, so let's look at three kind of simple examples. I do want to point a few things out to you. So first of all, these are all difference of squares problems because they all have two terms, 1, 2, 1, 2, 1, 2. They all have difference. Notice they all have a subtraction sign. And the terms that we're given are perfect square terms. Okay, so let me walk you through how to do these and what the pattern looks like. So this first one, x squared is a perfect term because we can write it as x times x. 16 is a perfect term because we can write it as 4 times 4. Now, when we break this apart, we're going to have two factors. And they are going to be, this first term that's split apart is going to become x times x in the first space. Now, the thing about 16 is this is not really a 16. You all know better than that. This is a negative 16. So negative 16 is going to actually be negative 4 times 4. So when I write my factors, it's going to be x minus 4 and x plus 4. Okay? And that it's kind of like a shortcut, and we can do some other ways about how to get there, but that is all you do to factor these. And the reason that it works, I will show you quickly why it works. When we multiply this back out just to check, we get x squared plus 4x minus 4x minus 16. Notice this plus 4x and minus 4x cancel each other out. So we are left with the x squared minus 16 that we started with. Okay, so if I use that same pattern to break up the 9y squared minus 1. Okay, 9y squared is 3y times 3y. Negative 1 is negative 1 times positive 1. So if I set my two factors up, that's going to give me 3y minus 1, and 3y plus 1. If you are a visual person and you need to see where those two things are going, the 3y's are both going to the front spot, and then I pull one of each of these 1's to go to the other part of the factor. All right, and so that's my answer. If I try this next one, that's going to give me 2x times 2x, and negative 25 is negative 5 times positive 5. So take a second to see if you can think about what those factors will be. They're going to be 2x minus 5 and 2x plus 5. And we could multiply all of these out, and the same thing would happen. The middles would cancel, just like they did on this first example. Anything that I multiplied would end up canceling. The other thing that I want you to note is all of these are all called conjugate pairs. And a conjugate pair is when you have the factor that looks pretty much exactly the same, except one of them is plus and one of them has a minus in the middle. Okay? And you will always get conjugate pairs with difference of squares. All right, let's look at some more examples. So these are actually some non-examples. And I want you to look back at your top 3 bulleted list on your notes and see if you can figure out why these are non-examples. All right, so hopefully you see the issue with this first one. It does have 2 terms, but the problem is this has addition. And when it has addition, we cannot factor that. So this problem right here cannot factor. And so you would just leave it like it is. That we can talk about in class kind of why that is. We'll discuss that. The second one, it does have subtraction, so that's a good thing, and it has 2 terms, but the problem is this term at the end is not a perfect square. I can't multiply 8 by anything or anything by itself and get 8 rather. So this is not difference of squares either. And the issue is that 8 is not a perfect square. All right, I'm going to do one example with higher exponents just so you've seen it. This is difference of squares because I have subtraction, so that's a good thing. And I also have 2 terms that are both perfect squares. All right, so thinking about what we did, that very first part of your notes where we looked at perfect squares, 100x to the 10th can be written as 10x to the 5th times 10x to the 5th. And 49, negative 49y to the 8th can be written as negative 7y to the 4th times 7y to the 4th. All right, take a second to make sure you agree with that. And now we're just going to use the pattern that we were doing just a minute ago to put our factors back together. So my factors are going to be 10x to the 5th minus 7y to the 4th times 10x to the 5th plus 7y to the 4th. All right. Okay, this last example is called multi-step. So when you first look at it, you're not going to see anything that seems strange. So we're going to identify again that this is subtraction. These are both perfect squares, so that's a good thing. So I'm going to rewrite what those are as perfect squares. So I know my first one is going to be 4x squared times 4x squared. My second one is going to be negative 9 times 9. Okay, so I'm going to write my factors. 4x squared minus 9 times 4x squared plus 9. Now, so far we have learned to look and make sure that there is no GCF on the inside of either one of these. And in that regard, we are good. There is no GCF inside of there, so we've taken care of that issue. Now, though, we know another factoring pattern, and that is difference of squares. And if you look at these 2 factors, one of these is the difference of squares. All right, this left one is difference of squares because it's got subtraction, right? And then it also has 2 perfect square numbers, which means this one can actually break apart again. 2x times 2x negative 3 times positive 3. And so this whole factored form is going to become 2x minus 3, 2x plus 3. All right, that is from this breaking apart again. And then that second one out here, this does not break down again, the one on the left, because it has the addition. It's stuck. So sometimes I will like write up here to myself that this is stuck and it can't keep going, which means I'm just going to bring that down. So it is part of my final answer, 4x squared plus 9. And if we did, in fact, multiply all of this out, we would get back to our original problem.